We have this quiz coming up on Thursday. So we're going to talk about section 2 in chapter 4 here today and tomorrow. Some review type stuff Wednesday, quiz Thursday, and then of course Friday's our calculus carol, extra credit opportunity. A few people have asked me, did it have to be like a Christmas carol? Could it be just some other type of song or poem or whatever? And yeah, that would be okay. And that's fine. It was something about the class, something about calculus, lyrics, those kind of things. Again, be original. There are some ideas you can get, tons of things out on the internet and stuff if you look for it. But use that to get an idea, but make it kind of personal, make it kind of towards more like our class, make it original. So that's kind of what I would hope, and that's kind of what I would expect for you getting some bonus points. Now, let's review here. I had this up the other day. So our quiz for Thursday will be over these two sections. In 4.1, you have to be able to match slope fields. And we did that on Thursday's homework in the book. Problem 7 through 14, we were doing that. Also on the worksheets, both of those worksheets had some sections where you had to match the slope field with the graph. We talked about if it only has x in the differential equation, you can tell because the slopes only change if you go across, or if you go vertically, that you get these slope columns where it doesn't change. I've talked to several people. Some people would rather think it changes as you go across when it only has x, and some people would rather look at it vertically, they don't change. Whichever, it's up to you. And then y's are the flip of that. And then if there's x's and y's in there, then it changes all over the place. When x's change and when y's change, the slope change. So you got to be able to do that. We got to be able to draw, like on the one worksheet where you had to draw those little slope segments. So you got to be able to draw a slope field. Okay, if I give you a differential equation. Oh, also on the matching of the slope fields, that's where we also sketched in our solution curve into there. If I give you an initial condition, you can sketch in your solution curve. So make sure you can do that. That's pretty. Just go with the flow of the slope segments. And then the other thing we did was Newton's law of cooling. Now we did those problems, and we'll have one more practice problem on Wednesday, and that was the y equals big T plus AE to the KT, and be able to solve that kind of a problem, that kind of situation. So number 23, number 24 on Thursday's homework were those kind of problems, the Boris and Natasha problem. Yeah. So make sure you can work out something using that. Okay, today and tomorrow we're going to be talking about this. Limits involving infinity. Okay, so we're going to be talking a lot about the idea of infinity next few days. And tomorrow we're going to talk about something called L'Hopital's rule. L'Hopital. I think that's French. L'Hopital. That's some guy's name. L'Hopital's rule. Okay? But that'll be tomorrow. But it also involves these limits involving infinity. So they seem quite different. They're two very different things. And that's the way Chapter 4 is. Chapter 4 is just applications of derivatives. So Chapter 4, each section is kind of its own thing, kind of an island unto itself that's unrelated to the other sections. The only thing they have in common, the only thing any of the sections have in common, is they involve the derivative somehow. They involve a derivative somehow. Differential equations clearly involve a derivative. Today, we're going to be doing these limits. We won't be talking about derivatives today, but when we get to L'Hopital's rule, it actually involves derivatives. Okay? And so, in Chapter 4, that's the common theme. What are the different things? Some are mathematical applications, some are real-life kind of applications. What are all the things we can do with derivatives? That's what Chapter 4 is basically about. All right. So, these are some things I jotted down about limits that we've already done. Okay? And we're going to add to this today. Okay? So, whether you write this down or not is totally up to you. But to me, this is the stuff we've already done back in Chapter 2 when it came to limits. So, we watch those videos about the diner. Where do the cars meet? Does the limit exist? That kind of stuff. And what we did is that when we were doing those limits, we basically arrived at 3 things could happen when you're doing a limit problem. Okay, so you're doing the limit as x approaches a, so x approaches 2, x approaches 3, whatever. One of 3 things can happen. Now, graphically, that's where we started with limits. We did graphs, and those were the easiest. I mean, because then you just imagine, do the cars meet? Do they not meet? Okay, and let me pull something up here. I'm sorry if you're writing that down. We'll get back to it here in a second. But if I go to something like this, remember when we did this, right? So if I have a graph, then limits are pretty easy. It's just do the cars meet? Well, the limit doesn't exist here. You know, here at 1, the limit exists. They meet right there. Okay? Same thing here. The cars meet at these different places, but here they don't meet. Even if there's a hole in the graph, we can talk about the cars meet. Even if there's a hole, that's the limit, right? But if the cars don't meet, then the limit doesn't exist. So if you have a graph, it's easy. But what we were talking about is what if you have an equation, right? What if you have an equation? How do you do the limit? Well, what you do, if x approaches 2, what do? Plug in a 2, right? You plug in a 2 for x. Now, one of 3 things can happen if you plug in a 2. You plug in a 2 and you get a half or 7 or whatever. That's your answer. You're done. The limit exists, right? So direct substitution. So you plug in a number, it works, you get out a number, limit exists. The second thing that can happen is you get 0 over 0. We called that indeterminate. Indeterminate. It means we can't determine if the limit exists. It might. We got to keep going. And what did we do? Well, we did some algebra. We factored and canceled. We found common denominators. We did the conjugate method. Remember that stuff? That is not going to be a big part of, hardly a part at all of the quiz. Maybe the factoring. Might do some factoring. But this is not going to be like the last quiz where we had to do some of that algebra and that common denominator stuff. We're not going to worry so much about that. The bottom line is if you get 0 over 0, you got to keep going. The limit might exist. Okay? And then you factor and cancel. Then you plug in your 2. And then you get your limit off. Or the other thing that can happen is you get something over 0, like 7 over 0 or 3 over 0 instead of 0 over 0. In that case, we said the limit does not exist. And what was happening, I don't remember, I think we talked about this. What's happening is you're getting a vertical asymptote in that situation. You're getting a vertical asymptote in those scenarios. Okay? So the cars aren't going to meet because you're getting a graph that's going, you know, like this, and like this, maybe. You know, you're getting something like that. So the cars don't meet. Okay? All right, so those are the situations we've already kind of talked about. All right, what we want to do today is talk about these situations. So this is the new thing. This is section 4.2, limits that involve infinity. So there's 2 different situations. So let's talk about the first one, which is we've kind of already talked about, but we're going to go a little farther with it today. So just write down this first one. And then if you would get your calculators out, I want you to graph that function. Graph this fraction here. Now, that's not a very good picture, but are you seeing something similar to what I have up there when you graph it? Now, again, like we said before, if you have a graph of a function, limits are pretty easy. Okay? Just where the car is going. Are they meeting? That kind of thing. But if you don't, and that's what our quiz is going to be like on Thursday. It's going to be no calculator. It's going to be equations. We're going to be dealing with equations like these problems. Okay? But let's just in red here, we can just answer this question. So as x approaches 3, what would you say for this answer? You would say does not exist. The cars clearly don't meet at 3. Now, what we're going to add to this today is we're going to add the fact that we can't stop when it says does not exist. On the last quiz, I let you stop if it was does not exist. From now on, if we have a limit that does not exist, we have to explain why. Why don't the cars meet? Well, we got to look at the left car and the right car. Where are they going? So right under here, you notice I put as x approaches 3 from the left and as x approaches 3 from the right. So what's the car on the left? Where's it going? Negative infinity. What about the car on the right? The car on the right is going up, 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 up to positive infinity. So we have to have that as part of our answer too. So anytime we get a limit that does not exist, think about why it does not exist. It does not exist because the cars don't meet. Why don't they meet? Well, where's the one on the left going? Where's the one on the right going? We got to tell where they're going and show that they don't meet. Now, this is a little off the topic, or well, not off the topic, but I've got a slide here a while back. You don't have to write this. But what if you had this situation? You don't have to write this one down, but what if you had this situation, we said, what's the limit? It still does not exist, because do the cars meet? No. Now they happen to be going the same place, and here's where informal language gets you in trouble. Another thing we've said about limits existing is we said if the limit on the left is the same as the limit on the right. Well, here the car on the left's going to positive infinity, the car on the right's going to positive infinity, they're both going to positive infinity, so the left and right limits are the same. Well, technically they're not the same. Because what we mean by the same is we mean they're equal. They meet at the same place, the same number. Infinity's not a number. Now we're going to talk about infinity a lot today, and infinity's a tough subject. It's just this really bizarre idea. And we're going to talk about it. But we would not want to say, now what we would say is does not exist, and then we do the limit on the left, limit on the right, we'd say they'd both be infinity. But the cars are still not meeting. So there is no limit. Okay, so the limit technically here does not exist. Now we're going to watch a little one of those videos like we did with the diner, a new one with infinity, and we're going to talk about that as well. All right, anyway, back to this. So if we had the graph, that'd be pretty easy to see. But now what we want to do, let's do this in blue here. How would we do this same thing, come up with these same answers without using our calculators? Well, you tell me. So I got a limit as x approaches 3. So what's my first move? Plug in a 3. So 2 times 3 is 6. 6 plus 5 is 11. 3 minus 3 is 0. I remember from my notes back here. If I get a number divided by 0, that means vertical asymptote. That means does not exist. So as soon as I get 11 over 0, I can write down does not exist. But I'm not done. That's not good enough. I've got to check 3 on the left, and I've got to check 3 on the right. Now, how can I check 3 on the left without a calculator, without a graph? Well, I need to pick a number to the left of 3, but I don't think I want to pick 2 or 1. 2.9999, right? Because I want x to be approaching 3, but from the left. So that would be a number a little less than 3. So that's exactly right. I could think of 2.9999. Now you say, well, how can I do that without a calculator? Well, it's pretty easy. What's 2 times 2.9999? Almost, good, I like that language. Almost 6, right? We're talking about almost 3 times 2 is almost 6, like 5.999. Plus 5. almost 11. So we're looking at 10.99999. Now, to be honest, I could just call that 11. It's not going to matter. You'll see why here in a second. It's the bottom that matters. What's 2.999 take away 3? Right? And we don't care how many zeros. Matter of fact, sometimes you'll see me write 11. I'll just write 11 on top, and I'll write small negative. Just a really small negative. What's 11 divided by a really small negative? A really big negative, because this is positive divided by negative, right? So that's the real key here, is that it's a really small negative or positive. Well, it's 2.999, it's going to be a small negative. So this divided by a really small negative is a really big negative. Negative infinity. Sure enough, that's what we had over here when we did the graph. Because now, and here's the part you're going to hear me say this a lot today. I know we're plugging a 3 in for x when we start the problem, but remember, a limit is not about when x equals 3. It's about when x is approaching 3. Because guess what? At infinity, we can never equal infinity. X can never be infinity. It can only approach it, get close to it. So when I talk about, so right here, when we had 11 over 0, we didn't have 11 over 0. What we had is close to 11 divided by close to 0. Close to 11 divided by close to 0, and getting closer to those. Well, what happens when the bottom gets closer and closer to 0? The fraction gets bigger, right? When the bottom gets closer to 0, the fraction gets bigger and bigger and bigger, going to infinity. The only question is it positive infinity or negative? In this case, it's negative infinity. Okay, and now, what would we do for 3 from the right? 3.0001. So we would plug in a 2 times 3.001 is a little more than 6, plus 5 is a little more than 11. Doesn't really matter, just call it 11. But the bottom is 3.001 minus 3. That's a very small positive. It'd be like 0.001. Small positive. So 11 divided by a really small positive is a really big positive. Positive infinity. So we can get those same answers in blue as I got in red when I did the graph. We can get those same numbers by plugging values in. The key is understanding from this page, if you plug in and get 11 over 0, you understand you're looking at a vertical asymptote situation. You're looking at it does not exist. So you got to check the left and the right. So this is just a little bit of an extension from what we've already been doing in Chapter 2. Okay, in Chapter 2 we just stopped with does not exist. Now we're investigating a little farther. All right, now, let's talk about number 2 here. We have 2 examples. Same function, what we're talking about is x approaches infinity. Now that's brand new. Here we're talking about the outputs going towards infinity. With a vertical asymptote, you're talking about the outputs going to infinity. Now we're talking about the inputs going to infinity. See the difference? So what we're saying is, what are these y values when x is getting really, really big? Well, first glance, you might say, well, plug in infinity. Now, you're going to hear me say this a lot today. Infinity is not a number. But it kind of acts like a number. I mean, you can do some things to it like it's a number. You just got to understand that in some cases it's not. It's going to behave differently than a number. Okay, for example, right here. When x gets really, really big, what's happening to the top? Getting really, really big. It's going to infinity. When x gets really, really big here, what happens to the bottom? Still getting really, really big. Even though you're taking away 3, still getting really, really big. What's infinity over infinity? Well, you want to say 1, but is 0 over 0 1? Well, no, we don't know. It could be a lot of different things. Matter of fact, we'll get into that here a little later, but 0, 0 could be a lot of different things. Same thing with infinity over infinity. It is not 1, because there are different sizes of infinity. Some infinities are bigger than others. Do you know that's true? This one always blew my mind. Think of a number line. Think about real numbers like decimals. And it could be rational or irrational, like 0.1 repeating or 0.2 repeating or whatever. There are more numbers. There are more numbers, fractions, decimals counted, between 0 and 1 Think about this now. How many numbers are between 0 and 1 on the number line? An infinite. There's an infinite number of places on the number line in between 0 and 1. Okay? There are more numbers in between 0 and 1 than there are integers. How many integers are there? Infinite. And there's an infinite number of numbers between 0 and 1. There's an infinite number of integers, but there's more numbers between 0 and 1 than there are integers. Different sizes of infinity. I know. Bizarre. That's just one of the weird things about infinity. We'll talk about it. So there are different sizes of infinity. Now here's where I'll kind of ruin the surprise a little bit. Here's where derivatives are going to come in. I'm going to ruin the surprise right now. Okay, listen. What we're really meaning, remember, x can't equal infinity. Okay, right? And so we can't really treat it like a number. But what we're saying is x is getting bigger and bigger and bigger. So this is getting bigger, and this is getting bigger. But the difference is, which one's getting bigger faster? The top. How much faster? 2 times. Now what about the plus 5? The plus 5, it turns out, doesn't matter. The minus 3 doesn't matter. Now, in the derivative, they don't matter either, do they? And there's the connection. How fast is this getting bigger compared to this? Well, that's a rate of change. That's a derivative. So the derivative is going to evolve. That's what L'Hopital told us, and that's what his rule's about. But we're not going to do that yet until we just get a sense of these limits. So what is this limit? Well, let's go to our graph to help us. So let's go to the graph here. So as x goes to infinity, that means as this car is going out here, out here, out here, out here, out here, way out here, what's it look like the graph's getting closer to? The y value. I think if you look on your graph, I think it's 2. If you would trace way, 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 way out here, what you would find is this graph's getting closer and closer and closer to 2. Okay? And same thing at negative infinity. As this car goes way out here, way out here. Now, you can't have 2 cars coming in when you're doing infinity, can you? You can't come into the left and right from infinity, right? So when we do as x approaches infinity, we're talking about this car goes way, way out here. What's its y value? Well, the y value is getting closer and closer to 2. It's a horizontal asymptote. It's a horizontal asymptote. So before we had vertical asymptotes with this, as x approaches infinity, you're dealing with horizontal asymptotes. So if we want to add that to our notes from back here, if I wanted to write that in, so if I had a limit as x approaches infinity kind of problem, right, that's going to be a horizontal asymptote situation. Okay? So vertical asymptote was this situation on our normal limits. When we plug in a number and we get like 11 over 0, 6 over 0, we know we got a vertical asymptote. Does not exist. With limits as x goes to infinity, we know we've got a horizontal asymptote. Now, it might not exist. You might, like x squared. Is there a horizontal asymptote on x squared? What happens to x squared as x gets bigger? It gets bigger. It goes to infinity. We would say the limit does not exist. Okay? It doesn't go to a number. So we'd say the limit doesn't exist, goes to infinity. As x goes to, so it's possible the limit doesn't exist, but if it has a horizontal asymptote, that means that the graph's getting closer and closer to that, way out at infinity. All right. So back to this. So we know from the graph the answer is 2. So how would we get this? Well, you guys just kind of said it. You said the top is getting twice as big as the bottom. And we said the plus 5 and the minus 3 don't matter. Now let me talk about that another way. Let's talk about x being really big. This is the way I like to think about these problems. We can't really plug in an infinity, but we can at least think, what happens as x gets big? So we say, okay, x is getting really, really big. Well, on top, so let's say it's 1 million. So I'd have 2 million plus 5. Well, if I've got 2 million in my pocket, let's say I got 1 million in my pocket. I got a $1 million bill in my pocket. So the question is, does the 2 matter? I would say the 2 matters. Because if I got $1 million in my pocket and there's $1 million bill laying there, am I going to pick it up? I mean, let's say the wind's blowing, it's snowing like it is today, and it's blowing and going across the parking lot. Am I going to chase it? Yeah. I'm going to chase it like crazy, knocking people down, right? I'm going to get it. Because that's a big deal. I got $1 million in my pocket, so I'm rich already. But that's another $1 million. That'd be a big deal. So the 2 matters. So let's say I catch it, and I put it in my pocket, and then I see a $5 bill blow.
You'd be running for
Well, okay, I'm kind of a tightwad, so I'd probably be running for it. And my wife would be knocking me down for it. I'm telling you, she would really be going. But seriously, would the $5 bill matter? It really wouldn't matter. And now remember, a million isn't very big. We're talking about as x goes to infinity. Compared to infinity, a million is a tiny number. Tiny number. What if I had $1 billion in my pocket and $1 billion bill was blown? Well, yeah, I'd pay somebody. Give you $1 million. Give you $1 million to go get that for me. Okay? But I would go get that $1 billion bill because 2 billion is a lot bigger than 1 billion. So the 2 matters. The 5 really doesn't matter then. And matter of fact, I'm not sure you guys really even understand that. If I have 2 million, does the 5 matter? I would say not. But if I've got 2 billion, the 5 really doesn't matter. And if I had 2 trillion, and that's only 9 zeros, by the way, only, the 5 really doesn't matter. You guys got your calculators out. Let's do a little quick experiment. Type in 1,000,000, 6 zeros. And let's say you had $1 million and you were going to spend $1 every second. How long would it last? So let's say you're going to sleep 8 hours a day, so you're only going to spend it for 16 hours of the day. So let's take 1 million. So it'd take 1 million seconds, right? So how long is 1 million seconds? So let's do 1 million divided by 60. Hit Control Enter so you get a decimal. That'll give you your minutes, right? And let's divide by 60 again. That'll give you your hours. Right? And then let's divide by, what did we say, 16? So we got 16 hours in a day to spend it. What do you got? 17. 17 days. So $1 million, which is a lot of money. It'd be great to have $1 million. Spend $1 every second, sleep for 8 hours. You would have it spent in 17 days. So that's 6 zeros. Let's do 1 billion, which is only 9 zeros, right? So let's do 1 billion, do that same thing. Divide by 60, divide by 60, divide by 16. What do you get? Isn't it just that same number we had with 3 more decimal places attached? Yeah, so we really didn't do all that. But it just, but think about that. $1 million would be gone in 17 days. You just change that to 1 billion, because you hear about millionaires and billionaires, and they all sound rich to me. There's a huge difference. 17,000 days. Let's divide that by 365. How many years is that? Almost 48 years? Think about that. 1 million and 1 billion. That's the difference. From going 6 zeros to 9 zeros. The money be gone in 17 days versus 48 years. That's more than half your life. And what if we went to 1 trillion? Well, wouldn't that just add another 3 zeros? Instead of 48 years, it'd be 48,000 years. 48,000 years. Right? Christmas, Jesus was born 2,000 years ago. 48,000. What's that? Well, you know what I mean? But here's the point. Here's the point, guys. 6 zeros to 9 zeros to 12 zeros. What a difference that made in the size of that number. Almost unfathomable how much difference that made. And we're talking about infinity. 1 trillion is not a very big number. 12 zeros. Have you heard of a Google? Not the search engine. That's 100 zeros. Googol. Google. That's 100 zeros. And that isn't even that big a number. The biggest number I think they have a name for is a Googleplex, which is a Google of zeros, which is just beyond even comprehension. But you know what I mean? If you just go to 15 zeros, what did we say? 48,000 years? That 48,000 years. If you just go to 15 zeros, now you're talking about 48 million years. What do they say the Earth is? 4-point-some billion? 4-point-something billion years? So all we need is 18 zeros, and all of a sudden we'd be at 48 billion years to spend that money, which is older than the Earth, right? By a factor of 10. So it's just unbelievable how big those numbers get, how fast they are. So it is hard to imagine. Anyway, back, yes. A googolplex is a Google of zeros. It's that many zeros. So a Google would be 10 to the 100. And a googolplex would be 10 raised to 10 to the 100. Ten raised to 10 to the 100. It just said infinity in the calculator. 10 to the 100th or 10 raised to 10 to the 100th? It says infinity. Okay? So, yeah, I mean, at that point, very large numbers, that's the default of what it does. Okay, but now, how does that apply to this? So that's something we got to think about. So here's what I would like you to do when we think about these problems. Now we're going to see the video, and they're going to talk to you about degrees and the highest degrees, but that only works when you have these algebra type equations. Later we're going to get into some of these equations that have signs in them, e to the x's in them, and then that doesn't work. So you really have to think about the concept of what's going on here. So what you want to say to yourself in a problem like this is just say, okay, as x gets very big, this is going to get big, so big that the 5 doesn't matter. The $5 bill is blowing along, we don't even care about it. Okay, on the bottom, x is going to get big, 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 big. If you lose $3, who cares? It's insignificant. Because the size of this is so much bigger than this. So we can do this. And so what this problem reduces to is 2x over x. And what happens then? The x's cancel, and you get 2. So all you people that have wanted to cancel these x's, but you couldn't because of the plus signs, right? But you get in trouble when you cancel and you're not supposed to. Well, here's your thing. You can now do it, right? You can ignore the plus 5 and the minus 3, but it's only because x is getting large. If this problem said x approaches 2 or 3, then we would plug in a 2 or a 3. But infinity's different. So this is saying what's happening when x gets really big? Well, the 5 doesn't matter, 3 doesn't matter, we get that. Same thing actually is true on negative infinity. Okay? The 5 isn't going to matter, the 3 isn't going to matter. It's just at the top and bottom will each be negative, but it doesn't matter because the x's cancel and we get 2. And so that's exactly what we saw in the graph. Way out here, the graph's approaching 2. Way out here, the graph's approaching 2. That is our limit as x approaches infinity. But here's how we can do it without having a graph. I call it the high powers dominant. Okay? Now, one other story I like to tell with infinity, just to give you the idea of how crazy it is to think of infinity in different sizes of infinity. Doesn't really apply to necessarily how we do this limit, but just the idea of infinity. Let's say you had a hotel that had an infinite number of rooms. And just to make it easier to imagine, it's one story and one big long hallway of rooms. Starting with number 1, room number 1, and going on. And the hotel is full. No vacancy. Okay? There's somebody in every room. Okay? There's a transport. Right? So somebody checks in and they have to go to room 2 billion. Right? We could just boom, we transport them right to that room. Okay? Like a Star Trek. They have to have a big pool. Yeah, a lot of vending machines. The ice. Yeah. There's a long wait at the water slide. Yes. All right. Now, so infinity. Okay. So it's full. So let's say that somebody comes and wants a room. Okay. Now, one option, if somebody mentioned this the other class, they said, "Well, just build on another room." That would be an option. That would be an option. However, we can do it without building another room. And we can do it without kicking someone out. And without doubling up. Can we add one more person to the hotel? It's full. Every room has somebody in it. And one person comes and wants a room. No. Here's what you do.
Make the derivative.
It is full. There's somebody in every room.
Take the derivative. What about the derivative?
Infinity's not a number, but pick any number you want. Google plus 1.
Derivative.
Google plus 1. There's somebody in that room. Right? Here's how you do it. You get on the intercom.
Kick someone out.
Oh, no, that's like the fourth time somebody said that. Get on the intercom and you say, need your attention. Remember when you signed your agreement that you agreed to do this. We're sorry for the inconvenience. However, I need everybody to pack up your stuff and move to a room that is one bigger than the room you're in now. One number bigger than the room you're in now. Ready, go. So everybody, so if you're in room 837, you move to room 838. So everybody does that, right? Can't everybody do that? Assume it's right next door, right? Everybody can do that, and now everybody's in a room, and room number 1 is open. So that person goes to room number 1. So, likewise,
It was full, though.
it was full. Every room
How
had
did the
somebody in
in-person
it.
move?
Okay, whoa. What? Listen to what Ryan just said. How did the in-person move? There is no in-person. It's infinity.
But you said it was full.
It's full. That means every room has somebody in it.
Then how can they move to another room if it's full?
They move to a room that's one higher number than the one they're in. Everybody has a room number. I told you this was going to blow your mind, right? It's weird. It's hard to fathom. Every room has a number. And every room has somebody in it. So it's full. And so everybody moves to one room higher. There's always going to be a room higher than the one you're in. Right? And so room 1 is empty. That person moves in. Now 10 people come. We need 10 new rooms. Everybody moves to a room. Get on the intercom. Hey, everybody add 10 to the room number you're on and move to that room. So everybody move down 10 rooms. There'd be 10 empty rooms. So 10 new people come in. So in other words, infinity plus 10 is infinity, right? That doesn't make sense because with regular numbers you can't do that, right? That's why infinity's not a number. It's more of an idea. Okay, but that isn't even the craziest part of this problem.
Yeah, the reference
Now they handle that all by computers. Remember, we have a transporter to transport, so we take care of all that internally. It's fingerprint. It's a fingerprint. All right. So here's the next thing. So now it's still full. Every room's got somebody in it. Big bus pulls up. Big bus. It's got an infinite number of people in it. The bus pulls up and it's got an infinite number of people in it. They get off and they want an infinite number of rooms.
I feel like that'd be really hard to do.
That looks like a transporter. We transport away. That's like the GU Street. You're right. We need an infinite number of empty rooms. Can we do it?
Yeah.
How?
Move everyone.
You can't do it the way we were doing. You can't say, hey, move down an infinite number of rooms. You can't do that. Add on a second floor. Okay, that'd be one option.
Just keep moving.
No, you never get there, so we're not going to make them do that. Say it again. Attention, everybody. We need you to please take your room number, multiply it by 2, and move to that room.
So all the odd numbers are 3.
Room number 1 moves to 2, 2 moves to 4, 3 moves to 6, 4 moves to 8. Now, I know room 2 million is going to have to move down to room 4 million, but we got the transporter thing, so they'll be fine. Okay? All of the what?
All the odd numbers are 3.
All the odd number rooms are now free because there's an infinite number of evens and there's an infinite number of odds. So all the people are in the evens, the odd ones are free, those people move in. All right, infinity. Unbelievable. All right. Videos. All right. So, remember we talked about these videos earlier. We went through these ones. When does a limit exist? And we talked about the cars meeting, the diner burning down, that kind of thing. Okay, now we want to go through the same process with infinity. Now, what you're going to see in most of this is a rehash of what I talked about up here. But I think it's good, now, especially since we've talked about this other stuff, it's good to see this again now. So you're going to see a little bit of this. Now, they don't go into this depth. They do it more with graphs. But again, just to kind of, since we've done all these kind of mind-blowing things here we've talked about, just a time to soak in what we've talked to up to this point. Okay? So let's take a look at what they had to say with this.
In this section, we'll delve into the mysterious and ancient relationship that exists between limits and infinity. As you calculate various values of f and evaluate different functions, you can come across some bizarre things. For example, take a look at this function. F of x equals the fraction 2x plus 1 divided by the quantity x minus 3. Now, if you plug in 3 to this, you're going to get 7 divided by 0. Now, I know we've seen 0 divided by 0 in a lot of previous examples, but we've never seen a non-zero number divided by 0. Well, that's bizarre, I know, and it indicates something important. In fact, whenever you substitute a number into a function and get a non-zero number divided by 0, it indicates the presence of a vertical asymptote. And this holds true for this function. Let's take a look at the graph of f at x equals 3. Now remember, an asymptote is a line which a function cannot reach. Here we have an asymptote at x equals 3 because when we plug 3
Just
into
like
f,
what we did,
we
except
got
they put a 1 instead of a 5. I
constant
guess I
divided
forgot.
by
I
0.
thought it was a 1.
Now, by examining the graph of f, we can see that the limits as x approaches 3 from the left and right are different. As you approach 3 from the right, f gets infinitely large, so we can say that the limit as x approaches 3 from the right of f of x is infinity. However, as you approach 3 from the left, f of x gets infinitely negative, so we say that the limit as x approaches 3 from the left of f of x is negative infinity.
Okay, so that's basically what we did with the graph. And then what they didn't talk about, which we went into, is if you actually plug in a 2.999 or plug in a 3.001, so you actually plug in numbers from the left and the right of 3, you can still figure out that it's infinity or negative infinity because the bottom is getting really small, okay, going towards 0.
Vertical asymptotes aren't the only asymptotes which relate to infinity. Horizontal asymptotes do as well, just in a slightly different way. To see this, let's look at the graph of f again. Now, as x gets infinitely large, or as we go along the x-axis, note that the graph of f is bending slowly downwards towards a height of 2. Now, if a graphical argument is not enough for you, take a look at this chart based on the function values of f. As x gets larger,
That's what we're talking about. You
f
can trace
gets closer
on your
to 2.
graph.
Now, mathematically, this means that the limit as x approaches infinity of f equals 2. By the way, the limit as x approaches negative infinity of f also equals 2. As we travel left along the x-axis, the function approaches the same height.
And remember, we talked about horizontal asymptotes. You actually can cross a horizontal asymptote, so that car could go up above 2, and then it could come back down. All we care about is what is it approaching when it gets way out here as x goes to infinity. So it's okay to cross a horizontal asymptote. You never would cross a vertical asymptote because the function's undefined there. So there would never be a y value there. But horizontal asymptotes, it is perfectly fine to cross them. It's just what's happening way out towards infinity to the right or to the left. This is where it talks about the degrees.
I said that x was getting infinitely large.
We'll compare it to how we're going to think about it.
Mathematically as the limit as x approaches infinity. Now, this type of limit is called a limit at infinity. If this limit exists for a function, then that function possesses a horizontal asymptote at the height given by the limit. Now, that's a lot of gobbledygook, but it's very simple in practice. Limits at infinity are very easy to calculate. All you have to do is compare the degrees in the numerator and denominator of the given function. By the way, the degree is the highest exponent.
That only works if you have
So if
polynomials.
we take a look at f again, we'll notice that the highest degree in both the numerator and denominator is 1. Because remember, if we don't write a power, it's inferred to be 1. Now in this case, the degrees of both the top and the bottom of the fraction are equal. And therefore, the limit at infinity of this fraction is going to simply be the coefficients attached to those highest degrees. Again, sounds like a lot of gobbledygook. We just take the coefficients of those x terms to make up the limit. Therefore, the limit will be 2 over 1. And we say that the limit as x approaches infinity of 2x plus 1 divided by x minus 3 is 2. And remember, we already know from the graph of f that the horizontal asymptote is 2, so it checks out. Now what happens if these degrees are unequal on the top and bottom of the fraction? Well, if the denominator's degree is higher, then the limit is 0. But if the numerator's degree is higher, the limit doesn't exist because it's infinity.
Okay, so they really kind of blew through that really fast about the higher degree. But that we're going to talk about that, and that's where we were saying about the rate that they get fast, or the how big the top is getting compared to the bottom, that kind of thing. Okay, there's one they kind of summarize here.
In conclusion, if the limit as x approaches c of f of x is infinity or negative infinity, then f has a vertical asymptote at x
So
equals
that's
c.
like you get 11 over 0, something like that.
Whereas, if the limit as x approaches infinity of f of x equals d, then f has a horizontal asymptote at y equals d. One word of caution. When we say that a limit equals infinity, we're actually saying that that limit technically does not exist, because limits have to be a real number. Therefore, it might be more enlightening to say that the limit does not exist because it increases infinitely, rather than saying that the limit equals infinity.
Okay, and that would be true. And I would mention that earlier. If we get a 7 over 0 or we get something like that, then, you know, when we get this situation, we're not going to say infinity here. Or we get this situation here, x approaches 3. We're not going to say the limit is infinity. We're going to say does not exist because they don't meet at a number. And then we will say from the left it's infinity, from the right it's infinity. We can say that. But we would say the limit does not exist. We wouldn't say it equals infinity. Because, like he said, a limit has to be a number. Okay? So it would be does not exist. Infinity is not a number. All right. So let's investigate what it is they were talking about with this thing with degree and so forth. So we're going to do 3 problems here that kind of have this idea of polynomials in them. All right. So we'll just do one at a time here. So you can just write each one down as we go. Okay. So here's the first one. So now we're going to be talking about that thing we were talking about earlier with big numbers, and what number is big compared to another number. Like a trillion is really big compared to a million, right? 12 zeros compared to 6 zeros. It's a huge difference, right? And as x gets bigger, that difference gets even bigger. So on this first one, what you would look at on a problem like this is you'd say, okay, as x is getting really big, well, clearly the top's getting really big, and so is the bottom. I mean, think about it. This is x cubed. Now, I guess we should talk about this real quick. If x is really big, like a million, you take a million cubed, but then you take away a million squared. Is that still really big? Yeah, because a million cubed, that'd be like 6 zeros cubed, that'd be 18 zeros. Compared to a million squared, that'd be like 12 zeros. And so there's still a huge difference there. And if x keeps getting bigger, then that difference gets even bigger and bigger. And of course, you know what a cubic looks like. It goes up and it goes on forever and ever and ever. So this cubic, this is going to keep getting bigger and bigger and bigger, even though you're subtracting. And as x gets bigger, you're subtracting a bigger amount. It's not near as big as this amount. So the term I use a lot is high powers dominant. So in this problem, not only does the plus 7 not matter, I'm not going to go chase down a $7, that's blowing in the wind. I'm not even going to chase down 2 million squared. If I got million cubed or 3 million cubed, that's so much more than a million squared that the million squared eventually becomes insignificant. Now, at a million it might not be, but at a trillion, the bigger it gets, the difference between x cubed and x squared keeps getting bigger and bigger and bigger. So there's another weird one. What's infinity minus infinity? Well, sometimes it's infinity, because that's what you got. X cubed is infinity, x squared is infinity as x gets bigger, but the difference between them is getting bigger and bigger. So infinity minus infinity might be infinity, right? Might be 0. X squared minus x squared is 0, but it might not be. All right, so kind of strange. Infinity over infinity, again, is not 1. We're going to add, matter of fact, tomorrow we're going to add this to our list of indeterminate, right? Infinity over infinity is like 0 over 0. We don't know. We don't know what the limit is. Matter of fact, we're going to see 3 of them in this page that are all different. Okay, infinity over infinity is not 1 because they're different sizes of infinity. All right, so on this one, we look at the bottom, we say, hey, those don't matter either. The only thing that matters is a high power on top, which is 3x cubed, and the high power on the bottom, which is 6x cubed. Now, what's that reduced to? 1/2. There's your limit. The things I crossed out don't matter when x is getting really big. Now, if this limit was x approaches 2, we'd have to plug a 2 in for x and do it that way. But when x is getting big, the high power is going to dominate everything else. The other stuff won't matter. The x cubed. So this is where on the video they were saying, if the degrees are equal, just take the coefficients, and that's your answer. All right, here's another one. Again, the top is getting big. The bottom is getting big. But what can you tell me about the top and the bottom as far as how big they're getting? The top's getting way bigger. If you look at the top, those two don't matter. If I look at the bottom, these two don't matter. Right? We look at the top and bottom separately, by the way, when we're asking ourselves that question. All right? The only thing that matters is the highest power on the top and the highest power on the bottom. But look at the top. It's x cubed. The bottom is x squared. Now, we can just do this. We can go 3x cubed over 4x squared. The rest of it doesn't matter. Now we can simplify that. What's that? 3x over 4. Now what happens to that as x gets really big? It really gets big. It goes to infinity. Now, we would have to say does not exist here. And then we could have infinity there as well. That's our explanation of why it doesn't exist, because it's not going to a number. So those two together would be your answer to that. That would be does not exist, and it would also be answering the why it does not exist, because it's going to infinity. So there we had infinity over infinity that ended up being infinity. Why? Because the top infinity was way bigger than the bottom infinity. And as x kept getting bigger, the top kept getting bigger and bigger compared to the bottom. So when you have a fraction where the top is bigger than the bottom and getting bigger, the fraction's getting bigger. All right, and then what happens on this last one? Again, both the top is getting big and the bottom's getting big as x gets big. So it's infinity over infinity, but what's happening? The bottom is getting bigger, faster. So we got like 2x squared over 3x cubed. Now that reduces to what? 2 over 3x? So as x gets big, the bottom is getting big. What happens to a fraction when the bottom gets big? It approaches 0. The fraction gets smaller. So there you go. We had 3 situations there where the top was getting big and the bottom was getting big in a fraction. However, what mattered was how big they were getting compared to each other. And that tomorrow is where we'll talk about derivative, the rate of change. But for now, we'll just reason it through in our head. So, number one, the top and bottom were both reasonably getting big together. The difference is the bottom was twice as big as the top, so it was 1/2. Second one, the top was getting way bigger, so that made the fraction get bigger, go to infinity. The third one, the bottom was getting bigger, so that made the fraction get smaller, it would go towards 0. And that's what they were saying in the video. All right, but what they were saying in the video would not help us do these. So let's do these. And there's going to be a few of these on your homework too. This is mostly what your homework's going to look like, is these x to infinity kind of problems. So we have to know something about these functions, think about these functions, and so forth. Now we notice we have an exponential. Now let me make a little side note here. Let me do this in red. Let me make a little side note. You can two to the x and x squared. Now both of those are getting big. I mean, 2 to the x goes up like that, x squared, goes up like that. So they look very similar. So as x gets bigger, both of these get bigger and bigger and bigger. Million squared, trillion squared, 2 to the million, 2 to the trillion. Which one is bigger? And which one's getting bigger faster? Exponential functions, no matter what the base, assuming they get bigger, base greater than 1, okay, are going to get faster than any power function. We could even have that x to the million or x to the billion instead of x squared. Eventually, 2 to the x would get bigger. It may take a while. If you had a x to the million, that would get big pretty fast. Eventually, though, 2 to the x would get bigger, faster. Exponentials get to the point where they're going almost straight up. Where x squared or something to any power is just going to keep climbing a little more steadily, but not quite as big. There are some problems where that shows up, I know, on the AP test and the multiple choice where you have comparisons and functions like that. You just have to know that. You just have to know exponential functions are going to grow faster than power functions do. And then the reverse is true on their inverses. If you have a natural log function which does that, compared to a sideways parabola which does that, this one is going to level off sooner than this one. This one's just never going to, I mean, they're going to continue to keep going up. It doesn't ever totally level off, but the log function is going to get flatter than the power function, the square root type function. Okay? So those are just some things to know about. It's called relative magnitude, right? Relative size. All right, let's go to this one. So x approaches infinity. What happens to this as x gets really big? Just this part right here. Gets really big. I mean, you only have 2 choices to answer, you guys. It gets really big or gets really small. Those are your 2 choices. So when I say what's happening to this, it's going to be one of those 2 things. Right? What happens to e to the negative x when x gets really big? Gets really small. And really small to us means 0. Right? Because e to the negative x is 1 over e to the x. So when x gets really big, it's kind of like having 1 over infinity. Well, for our uses, 1 over infinity should make you think of 0. 2 over infinity, 3 over infinity is 0. A number over infinity is 0. Because, now, again, I'm treating infinity there like a number even though it really isn't. When I say 1 over infinity is the same as 0, what I'm saying is 1 over a really big number is a really small number. 1 over a really big number is a number getting close to 0. That's what I'm really saying. All right. So infinity minus 0, that's just infinity. And then what's happening to the bottom? When x gets big, what's happening to the bottom? Getting really big. So again, we have an infinity over infinity situation. But does that mean it's 1? No. We keep going. We reason through it. So what we have is, if this is going towards 0, isn't it really just insignificant? This part's just not mattering when x gets really big. So we end up with e to the 3x over 4e to the 3x. Well, now what can we do? Cancel, and we get 1/4. E to the 3x's would cancel, and we get 1/4. So sometimes we get an answer. Now, what might have happened there is I might have had this instead. What if I had e to the 4x over 4e to the 3x? What if I had that? You would subtract the powers, you'd have e to the x over 4. Now what happens to that as x gets big? Infinity. Now remember, we can't just say infinity, we'd have to say does not exist also, right? The limit would not exist. Because the top is getting way bigger, the bottom's just 4. So we have this huge, huge number, divided by 4, which is just getting bigger and bigger and bigger. So it's possible we could have had this, and then things wouldn't have just canceled. We'd have that. So it's similar to what we had on the other page as well. The top getting big, bottom, maybe we can do some simplifying, that sort of thing. Okay, let's do this last one here. As x gets big, what happens to sine? Oh, see, now I lied to you. I just said the answer is always going to be gets really big or gets really small. It's between 1 and -1, right? Sine is going to be between -1 and 1. It's just going to kind of bounce back and forth. You go out forever out to the right on sine, it just kind of bounces back and forth, -1 to 1. Okay? What's happening to the bottom? Getting really big. So this isn't an infinity over infinity, but what would it be? -1 to 1, kind of those numbers in between there, over a really big number. The answer is going to be 0. Right? Basically what you have is a fraction where the bottom's getting really big, and the top is not constant, but it's kind of, it's like it's constant. It's just kind of hanging out there. Now, here's what's interesting about this. If you graph this, we talked about how you can cross a horizontal asymptote. That's what's going to happen here. Yeah, because you're going to get a number up here that's switching from positive to negative divided by a great big positive. So this is going to switch from positive to negative. So what's going to happen is it's just going to keep getting closer and closer to the x-axis, like that. It's just going to keep, right? That's not very good drawing. But if you were to graph this function, you'd see out here that it's just crossing, but yet it's getting closer and closer and closer to 0. But it is going to be 0 a whole bunch of times. Think about it. The top's going to be 0 a lot. And you have 0 divided by something, which is 0. So it's going to cross a whole bunch of times. But the horizontal asymptote is still 0. The limit is still 0. So we can do that without looking at a calculator. We can just reason our way through it. What's happening as x gets bigger. All right, let's finish up with a couple of ideas here to kind of summarize some of this. And some of this we'll save for tomorrow. All right, so we had mentioned you don't need to draw this graph because like we were saying earlier, graphs are pretty easy. So this is similar to the graph we had earlier. The only difference is I put a hole in it, okay? Because we're going to do an equation that looks like this here in a second. So if I ask you for the limit as x approaches 1, so let's talk about all the different type of limits we've had. So the limit as x approaches 1. What would you say? 1/2, right? Limit as x approaches 1 would be 1/2, right? The cars meet right there. When we got a graph, it's easy. Then another one we could talk about is the limit as x approaches -1. Does not exist. And then when you do -1 from the left, which would be infinity, -1 from the right, which would be -infinity, and there would be your answers there. And then the last one, and the newest one that we just learned today, the limit as x approaches infinity would be 1. The cars, as they go way out to infinity or out here to -infinity, they're approaching a limit of 1. Okay? And so that picture kind of summarizes the different things we've done. Now, when you have a graph, it's pretty easy. Okay? What about an equation? Well, we've talked about some equations here with the x approaches infinity stuff. Okay? Let's go back and review real quickly those two scenarios up here. Okay? So the last problem, two problems I'd like you to put on here, put on your paper, would be these two right here. So we're kind of coming back full circle. So we started out talking about limits as x approaches like 3, that kind of thing. Then we went to this new idea, what about when x is getting big? What about when x approaches infinity? And now we're just going to kind of circle back and do a couple of these again. Okay, go ahead and do the first one. We got an answer for the first one? 4? 1/4. Yes, 1/4. And what'd you do? Factored it, right? Well, hopefully you plugged a 2 in first. X approaches 2, you get 0 on top, you get 0 on the bottom. That means keep going, right? 0 or 0, that's indeterminate. So we say, now some of you might have skipped right over that because it was so obvious that we're going to factor. So x minus 2, x plus 2, the x minus 2's cancel. You get 1 over x plus 2. Now you plug your 2 in, and you get 1/4. So that was one of those, we said we'd stick with some simple algebra probably right now, but we could have done a common denominator one or a conjugate one. That's what we had done earlier in chapter 2. So you plug in, you get 0, 0, keep going. There's some sort of algebra you might have to do. If we go back to our first page of notes today, we talked about that right here. You plug in, you get 0 over 0, keep going. The limit might exist. You see what you get. Now that would be the similar situation to this right here. It would be a hole in the graph. That's what 0 over 0 is. So that would be similar to where we said here, as x approaches 1, the limit is 1/2. It's undefined because when you plugged in a 1, you get nothing. Just like here, you plug in a 2, you get undefined. There's a hole there, but the limit does exist. The cars do meet. All right, now we try -2. What do you get when you plug in -2? Well, you get -4/0, right? Which we learned already. When you get that, right away you put does not exist, but that's not enough. Right? And this, I'm going to add one to your homework from your book, because your book didn't get into any of these. Your book signed, so I'm going to add one. It's going to be very much like this one. So what do we have to do from here? -2 from the left, -2 from the right. Because what do we have happening on the graph here? We have a vertical asymptote. Remember what we said in our notes back here? When you get a 7/0 or a -4/0 or something, you have a vertical asymptote. That's what's going on here. Okay? So we know we have a vertical asymptote. So we've got something going towards infinity. We just got to figure out if it's positive or negative. So -2, what would be left of -2? 2.0001. So we put that in. Oh, you know what would be nice? Did anybody factor this one already? You wouldn't have to, but this would be nice to have factored it already. Because if you factored it, right? If you factored it, now it's just easier to plug into. Now I don't have to take -2 and square it. Now if I would, -2.001 squared would be like 4.00001 minus 4, so it's going to be a really small positive. So it's going to be -4 over a really small positive. Now if you had factored it already, like this, think about this now. If you plug -2.01 into this, plus 2, what do you get? Really small negative. So you get 1 over a really small negative. Well, either way, that's going to come out -infinity. So either way you do it, if you factor it first or not, you should get -infinity for that first one. Now, -2 from the right would be like -1.999. If you plug it into here, you'd square it, which would be just short of 4, minus 4. So that'd be like a small negative on the bottom. So you have a small negative and a -4 on top. So that's going to be a big positive. Negative divided by negative. Divide by a really small number, it gets big, and it's going to be positive. Or if you put -1.999 into here plus 2, that'd be a really small positive. So it'd be 1 divided by a small positive. Again, positive infinity. So here's your answer. Does not exist along with those two pieces of information. Okay? So that's similar to what we did earlier. All right, so a lot of stuff thrown at you. All this infinity stuff makes you go crazy a little bit. And then you've got these limits. So with the time that you have left, last 20 minutes or so, we'll go ahead and if you need this assignment sheet, let me know. If you had some questions on the worksheets or something from Friday, this would be a time to work together and talk to each other and ask me if you want to. But it's this line right here, 4.2, day 1. And I've got a few extras of the assignment sheet if you didn't pick one up on Thursday. I think that's when I handed them out. So 4.2, day 1, 9 through 21 is just some limit problems. And then do this limit problem right here also. Okay, it's just an extra one that I've added on.